Injecting social diversity in multi-objective genetic programming, the case of model uniformness rule learning. Model-driven engineering advocates for the use of models as first-class artifacts in software developments instead of raw codes, combining domain-specific modeling languages with transformation engines to facilitate the creation and management of complex systems. However, despite its promise, MDE faces challenges, particularly in automating tasks like ensuring the well-formed of models, which traditionally require manual effort from trained personnels. To address this challenge, the authors propose leveraging genetic programming, especially multi-objective genetic programming, to automatically learn model well-formed rules from examples. Genetic programming has shown promise in automating tasks based on examples, but it suffers from issues like converging to a single fitness peak and unnecessary growth in solution size. The research aims to inject social diversity into evolutionary computation process to improve the efficiency, convergence, and generalizability of GP in learning well-formed rules. The author introduced the social semantic diversity measure inspired by natural language processing techniques to indirectly promote semantic diversity among individuals in the GP population. The paper presents two approaches to integrate SSDM into the genetic programming framework as an additional objective and as an alternative to the traditional crowding distance. In both cases, social semantic diversity measure computation remains the same, focusing on evaluating the contributions of individuals to the overall fitness of the population based on their performance on example sets. This evaluation of the proposed approaches involves addressing several research questions. Firstly, the authors investigate whether the results are due to efficient exploration of the search space or the sheer number of individuals considered during evaluation. Secondly, they examine whether employing SSDM as an objective improves the search strategy and to what extent. Lastly, they explored whether the using SSDM as an alternative crowding distance enhances efficiency and generalizability compared to using it as an objective. To, to evaluate these questions, the authors conducted empirical evaluation using three meta models: family tree, state machine, and project manager. These meta models represent varying levels of complexity, allowing a comprehensive assessment. Also, the example sets are consist of 20 models for training set and 100 models for the test bench. The result of the evaluation demonstrate significant improvements in efficiency, convergence, and generalizability when employing SSDM in GP uh, framework. Efficiency shows a significant improvement when SSDM is used, as can seen in the columns here. The number of generations required to find a solution when employing objective is a lot smaller than when employing standard. Moreover, utilizing SSDM as an alternative crowding distance exhibit even greater efficiency without compromising the generalizability. The strengths of this paper, I would say, are novelty, empirical evaluation, and clear presentation. The paper introduces a novel approach integrating social SSDM into genetic programming for learning model informedness rules in model-driven engineering. This novel approach addresses an important challenge in MDE. The paper provides a thorough empirical evaluation addressing multiple research questions and demonstrating the effectiveness of the proposed approach. Also, the paper is well organized and clearly presents the problem statement, proposed approach, and experimental setup, result, and conclusion. As for weakness, the paper has limited generalizability, lack of real-world application, and assumption. There are some assumption and limitations. So, while the empirical evaluation demonstrates the effectiveness of the proposed approach across three meta-models, the generalizability of the findings to other MDE scenarios may be limited. Also, the paper focuses on theoretical aspects and experimental validation within a controlled settings. The real-world scenario applicability and scalability of the proposed approach to large-scale model-driven engineering projects are not thoroughly explored. As for limitations, the paper assumes certain conditions and constraints, such as use of specific meta models and example sets, which may not fully represent real-world model-driven engineering scenarios. In conclusion, the research paper offers a novel approach to enhancing the effectiveness of multi-objective generative programming in learning model mindfulness rule in model-driven engineering. By introducing social diversity through SSDM, the authors have demonstrated significant improvements in efficiency, convergence, and generalizability of generative programming-based learning approaches. As for future research, they could explore the application of the proposed approach to other model-driven engineering scenarios, such as model transformation learning or code generation. And that's the end of my presentation. Thank you.